Hey everyone, and welcome to This Explainer. Today, we're giving you a debugging toolkit a serious upgrade. Look, if you're in IT support, DevOps, or software engineering, you already know that time is literally your most precious resource during an outage. Every minute counts. So we're going to master HTTP status codes together, turning them from these kind of cryptic, annoying numbers into a superpower that will drastically reduce your mean time to recovery.
Let's be real for a second. Have you ever spent an hour anxiously restarting back-end services, checking database loads, just pulling your hair out over a 502 bad gateway, only to find out way later that it was a simple proxy misconfiguration? Or maybe you escalated a ticket to the back-end team, only to be politely told it was a client-side error all along. Yeah, we've all been there. Misreading an HTTP code sends you running in the exact wrong direction, wasting hours and just extending those stressful outages.
So, here's our game plan for today. We'll start with the cost of misreading codes, then dive into the 4xx client-side errors, followed by the 5xx server-side errors. After that, we'll untangle the most confused code pairs, walk through a real-world scenario of fixing a 422 error, and wrap it all up with a handy final cheat sheet.
All right, kicking things off with part one, the cost of misreading codes, because time is absolutely precious.
To start, let's build a rock-solid mental model. The foundational heuristic you should always rely on is the you messed up versus we messed up rule. It's that simple. If the code starts with a 4, it's a 4xx client-side error, meaning the client, whether that's the browser, a mobile app, or an API caller, did something wrong. They sent bad syntax, they don't have permissions, or they're asking for a page that literally doesn't exist. You messed up. Now, if it starts with a 5, it's a 5xx server-side error. That means we, the infrastructure or application owners, messed up. Our server crashed, our proxy's busted, or we're just totally overloaded. Keep this framing in your head at all times.
Let's move to section 2 and see how this builds. 4xx client-side errors. The client messed up.
The classic 400 bad request. Think of this as a total structural failure. Imagine a client sending a JSON payload but forgetting a closing bracket, or formatting a URL entirely wrong. The server looks at that incoming request and basically says, I can't even read this. It violates the core HTTP syntax rules, meaning the server simply can't parse it to take any further action. It's stopped right at the front door.
Next up is the 401 unauthorized. Now, despite the name, a much better way to think about this one is unauthenticated. The server is essentially asking, who are you? The client either didn't provide a login token at all, they provided an expired one, or they just used completely invalid credentials. To fix a 401, it's pretty straightforward. The client must successfully log in and provide a valid authorization header.
Then we've got the 403 forbidden. This one means, I know exactly who you are, but there is no way you can do that. The client's identity is verified, sure, but their role or access level just isn't high enough. For example, trying to hit an admin-only endpoint with a standard everyday user token, boom, 403. Crucially here, having the client log in again won't fix this. Their underlying permissions actually need to change.
Let's rattle off 3 other really common 4xx codes you're going to see. First, 404, not found. We all know this one. It means the requested resource simply doesn't exist on the server. Next is 409, conflict. This pops up when the request conflicts with the current state of the server, like if you're trying to register an email address that's already sitting right there in the database. Finally, 429, too many requests. This means the client hit a rate limit. They're firing off requests way too fast and need to back off and wait before trying again so they don't crash the system.
Now, what's really fascinating about this next one, the 422 unprocessable entity, is that it actually originated from an extension called WebDAV back in RFC 4918. But today, it has become the absolute gold standard for REST APIs. A 422 happens when the JSON is perfectly formatted, so it's definitely not a 400 syntax error. But the data inside is logically invalid. Say you're submitting an order for -5 items. The server can read the request just fine, but it violates basic business rules.
All right, shifting gears to section 3, 5xx server-side errors. This is where we look at our own infrastructure faults.
The dreaded 500 internal server error. It is the ultimate catch-all. It means the server encountered a nasty bug, an unhandled exception, or a full-blown application crash, and it literally doesn't know what else to say to you. It's giving up. When you see a 500, your next step is almost always to dive straight into your application runtime logs to hunt down that stack trace.
Now, a 502 bad gateway, that is purely an infrastructure error.
It means your gateway or proxy, let's say Nginx, tried to talk to the upstream backend server, like PHP FPM or your Node app, and either couldn't connect at all or just got absolute garbage back. A 502 almost always points to a crash backend process or a misconfigured socket where the proxy and the application are just completely failing to talk to each other.
503 service unavailable is usually just a raw capacity issue. The server is technically up, but it's way too busy, totally overloaded, or maybe down for planned maintenance. A well-configured 503 response will actually include a retry after header, explicitly telling the client how many seconds they need to wait before trying their request again.
So the crucial point about a 504 gateway timeout is that it's purely about the ticking clock. The proxy is successfully connected to the upstream backend, sure, but the backend is taking way too long to process the request. Maybe it's stuck on a super slow database query. The proxy eventually hits its strict time limit and just drops the connection. Fixing this usually requires optimizing that backend performance, or sometimes adjusting proxy directives like proxy_read_timeout in Nginx.
Moving on to Section 4, the most confused code pairs, because mastering the micro nuances here is what separates the pros from the rookies.
First up, 401 versus 403. Let's actually pause here for a second because this highlights the fundamental difference between authentication and authorization. 401 asks, "Who are you?" and you fix it by providing valid login credentials. 403 asks, "Are you a lab?" Your identity is known, but you lack the role to view the resource. So remember this, logging in again fixes a 401, it does absolutely nothing to help you with a 403.
Next, let's look at the proxy pairs, 502 versus 504. A 502 bad gateway is a connection or format failure. Nginx reached out to the upstream, but the connection was refused or the response was totally unreadable, meaning the upstream likely crashed or is misconfigured. A 504 gateway timeout, on the other hand, is purely about time. The upstream is running perfectly fine, but is just so slow that it's exceeding the proxy's patience.
And this brilliantly illustrates the evolution of modern APIs, comparing 400 with 422. A 400 bad request is a syntax failure. The server cannot even parse the malformed JSON. But a 422 unprocessable entity? That means the JSON was perfectly readable, but the server rejected the semantic logic inside of it, like trying to purchase an item that's currently out of stock.
Okay, Section 5. Let's put this all into practice with a real practical scenario. Fixing a 42.
Picture this workflow. Step 1, you fire off a request in Postman or your browser's dev tools, and you spot a 422 status right there in the Network tab. Because you know it's a 422, you already know the syntax is fine. Step 2 is the absolute key to fixing this. You have to look at the JSON response body. Good modern APIs will return an errors array right there explaining exactly what business logic failed. Maybe it says, email must be a valid format. Step 3, you correct that specific semantic violation in your payload, resubmit it, and boom, you get a 200 OK. Triage complete. Finally, Section 6. Let's zoom back out and lock in this mental model with a final visual cheat sheet.
So here is the rundown you can literally screenshot for your daily debugging. 400, bad syntax. 401, need to log in. 403, lacking permissions. 422, valid syntax but invalid business logic. 500, server code crashed entirely. 502, proxy connection to the upstream failed. And 504, the upstream is just too slow. Keep this framework super handy. It's designed to be your instant, go-to reference for everyday troubleshooting.
So I've got to ask, are you still going to hunt for server bugs when a 4xx code is literally screaming that the client is at fault? By applying this structure, you finally stop guessing and you start actually diagnosing. How are you going to update your triage workflow today to ensure you're always chasing the right fix? Take this mental model straight into your next on-call shift and just watch your resolution times plummet. Thanks so much for joining me on this explainer. Keep learning and keep building.